One thing I wonder about the fact that I really cover the essence of the course, the essence which is really required to work on the stochastic process of structural system. So I really expect you to get some time to read, at least to turn the page which I assigned to you, the 4 of them. Then not just reading every page, at least to turn the page in the area. Then some problems that you can try out and get some concern. That's important, okay? So that's what I want you to do. Otherwise, I may not able to cover some good amount of the material. But after I developed this course already some years ago, and many students pass through, and I have a feel about what they think and all that. So I think you should understand, and if you can some area, then you see me. Youngbin came in a couple of times, about 3 times, asking some questions, but you do the same thing, would you? Then just feel free to walk into my office. Then I usually stay there in the office. Then you can talk or whatever, okay? And tonight, 진로 설계, what's the time? 5 o'clock or 6 o'clock? 5 o'clock. I'm going to give a talk in 진로 설계. Not the underwater explosion, not such a topic, about the life. So about my life, for last 70 years of my life, I'm going to talk about the fact. Nothing hide, just everything open. Then that's what I'm going to do. So if you have a chance, come in and listen what I did for 70 years, what would be my ordinary life. So maybe some of you may go through the same path that you are going, and maybe you plan to do so as an engineer. So I'm not demanding, asking, but if you have a chance, have a time, maybe stop by, listen, and ask questions. I didn't really write the stuff I would talk for an hour today. I gave a lot of thought. So then I'm going to start to talk at 5 o'clock. Then we'll share some of my good experience. And whoever wants to go study abroad, particularly in US, I can answer some of your questions which you might have interest to know, because I lived there for since 1965. That's a long time, isn't it? Since 1965, 75, 80, 95, 2005. It's about 45 years I live out there. Then I was in schools and all that, so you might have some questions. Any questions. Then some of the question I may not able to answer, then I can answer. But I'm pretty sure most of the questions maybe I could answer. That's what I'm thinking. Okay, so this is error in amplitude estimate, and the previous one was the statistical sampling errors. We talk quite a bit, and so this is the still same error criteria, but this is if you look at the table, this is from Bandet's application of correlation that assigned the book. Is random errors in the mean and the mean square value estimate. When you hear about the estimate, we are talking about the possible errors in there. And estimate and corresponding random error epsilon r. So this is the mean value estimate. This is a mean square value of the estimate. If you know mean and mean square, can you find the variance? Can you find the variance? Yes or no? I want you to look at this, think about the equation set, like a definition. Definition of what? The variance. Okay? Definition of the variance is expected value of x minus mu square. So I mentioned to you before already, but I'm reminding you all the time. So three unknowns there, the variance, mean, and also mean square value. If you know two, then third, you can find the value. This is a mean value estimate, and this is a possible error, and this is mean square value estimate. This is a mean square value estimate. You have a hat. That's what we are using it here. And arrow, the random arrow is here. So if you are interested on the details of the derivation for the random arrow, I'm going to ask you to consult the random data book written by Bandet's. So we'll just pass it through. But this is well known. So ensemble averaging, clear. This is a really discrete case. And this is a continuous case. It's one, the time history, the sample record, then you can compute the time average. If it's algorithmic, this is the one you can use it. If this is discrete, means for the stationary process at the given or any arbitrarily time t1, then you can determine for all xi. Xi means xi at time t1 and all that. And this is mean square estimate. You can tell this is square I. So stationary process, you can compute at the given ti if you're dealing with the event and the given arrows here. So as a good review, I'm going to talk about this, which will subsidize the equation shown here. The B here is a frequency, the bandwidth in hertz. So we're gonna talk about this using this. All records are statistically independent. X, Y are not correlated, which is independent. Does not affect each other, which makes all the equation very simpler. This is Fs is a sampling frequency. Sampling frequency is twice of a maximum frequency. Okay? Sampling frequency is twice of the maximum frequency. Why? The reason, one of the reason is to avoid or to prevent the so-called aliasing problem. Anybody heard about the aliasing problem? When you see the movie, in all the days, we use a film, 18 feet per frame, 18 frame per second, the film. In your era, you never saw film? In a movie film. You know what that movie film is? All the days before the video era came in actually a movie theater, they have a roll of the film. Roll of the film, they mount on the film projector, then they put the switch, then it rolls. Just between the lamp and the lens, then it rolls around. So you saw about that? Okay, you're in the super new era. It goes through, it clicks, frame, clicks it. It clicks 18 frames per second. And then in our eyes, when I take a picture, then get the frame behind our, what do you call, screen in the inside, it becomes look like a continuous. Okay? So, but if you all the days watch movie, like a Stagecoach is Youngmacha, then look like the wheel is rolling forward, but look like a wheel is going backward. So movie you might have experience, no? That effect is called aliasing. I made a copy to show you, but I want you to type this in your internet page. Then a lot of information is there, and I think it's a wiki encyclopedia. Wiki. Take a look at. I think it's a wiki encyclopedia. If you click it there, it explains quite a bit, but don't read all that long explanation. What this is, for example, this is very, very high frequency sinusoidal function with constant amplitude. This is sinusoidal function with F0 frequency, which is equal to 1/2. But this look like some lower frequency function. Okay, lower frequency function, such as like this. I'm just quickly. It's a little bit not exact, okay? But it look like if I just connect it, lower frequency function, Well, if you draw really well, it's going to be low frequency as the sinusoidal function. But this is high frequency. This guy is a high frequency, F naught, with the frequency is F naught. So this is one cycle. Okay, this is one cycle. But this low frequency is start here, ending here. Let's say, which is how many cycles are here? So 1, 2, 3, something like a 3.5 more. So which means this guy, if it's a 3.5 F naught, this guy is could be F. This is F naught. This is F naught. So I'm going to say this is F1. But such a high frequency sinusoidal function, you could think, when my eyes are taking pictures, about 3.5 times lower sinusoidal, because my mind doesn't work fast. It's much slower. So when it picks up, it pick up this, it pick up that, it pick up that, it pick up this, it pick up that. So even if it has to be 3.5 times faster frequency in reality, but my brain is acting like, oh, this is about the 3.5 times slower, like this, okay, as a mistake. In other words, in the stagecoach, or even car with some spoke in the wheel, it goes faster, but sometimes as they're moving fast, it looks like rolling backward, which means it's slower rate. That's called aliasing, and I want you to read the Wiki Encyclopedia to capture. They have nice pictures in there, then you can tell. So so you need the sampling rate is concerned, is just the picking, okay? So it has to be twice the maximum frequency, and the delta F is 1 over T. T is period. What's the delta F? The frequency step Fn minus Fn minus 1. We talked about that before. Then F max is equal to frequency step, frequency size, okay, times n over 2. N is number of data points. This is absolute signal processing rule. Why is n over 2? I said n is total number of data to processing it. If you look at the instrument, even if you pick n, it doesn't show the data for all the endpoint. No, because as you look at the Fourier transform, you need information on magnitude and phase. So you have to have the instrument or processing instrument should carry the amplitude data and also the phasing data. So if you have a total n number of data, it has to split into two. One group is to store amplitude. Another half should store the phase. So you need to always carry the amplitude transform. You need also the phasing transform. Two different information, right? Always. So always has to have storage is concerned 2 divided by n divided by 2. That much is stored. Even if you have a total n storage, you have to divide by into 2 to process it. Then you can throw into the frequency domain, then from the frequency domain to go back to the time domain, then you need 2 storage, right? That's the reason divided by half. So delta F is 1 over T. So from here, then Fs is 2 max, 2 times this quantity, so is equal to n over T. So that's why Fs is n over T. And the total number of data point here is, of course, this is a sampling frequency, multiply total time, then is equal to, this guy is 2 times F max times T. That's what the 2B T. So T is here, 2F max is, F max is B. This is really bandwidth, frequency bandwidth, you can tell here is from 0 to the maximum frequency. So when you do the Fourier transform, you have 2 set up. That's what we did. So this is F. This is a magnitude. Another setup. This is all frequency. This is a phasing information. Phasing information you need up to 180 degree, not 360 degree, because after that it's just to repeat the same thing. And so this is a total number of data point is n over 2. This is n over 2. I'll talk quite a bit more when you're getting into chapter 4. So that's what we're gonna do. But some appetizer. Okay. This is the area I always give one problem in the midterm exam. So this is really worth to pay attention on this. It's called change of the variable. Listen carefully. Change of the variable. Suppose that xk, k is a possible event. What does it mean, possible event? Something like a time, ti or t1. You have the ensemble. You are dealing with ensemble. All collection of the number of the random record. Whole bunch of record here. That at the given t1, when you say t1, at the x1 time situation, this is time t. This is like x1 data. This is all time domain, x2 and x3 all the way through. But for the given, you are looking at time t1, any arbitrary time, and you have the random, the record there, then you can pick this guy, pick that guy, pick this guy, pick this guy, is x1 at time t1. This is like x2 at time t1. This is x3 at time t1. Or you could simply say that this is like x1. For example, this could be x2. It's all talking the same thing over. Xk, k is possible event. This is one random variable. The whole thing is a process. So here, xk is a random variable. It's a random variable, not the process. That particular point, random, the variable. With the probability density function px, and y is gx. Y is a function gx, okay? Is any real single value continuous function of x. Y is equal to function of x. You can express, of course, as x. X is equal to the function g of x, g of y. So that's, but it will be clear when I do some sample problem, example problem. Consider the case where the inverse function, x is a function of y, is also the real single-valued continuous function. This assumption is very important. Over here is y is a function of x. Again, it said the real single-valued continuous function. Such an assumption is very important. It's not the discontinuous function, only valid for the continuous function, but also has to be single-valued. Single-valued function is, you have like that. This is x and y. Single-valued. I taught already. If I just pick the one point here, okay, so then it has only corresponding value has a 1 point. That's a single valued function. However, as we did before, one represent the whole situation because periodic function repeat. 1 point, I pick 1 point. So this is, say, x and this is y. This case is a single valued function. However, as it said, the inverse function x expressing as a y is also real single valued. It's a demanding, but as you look at here, this case is a single value. This is x1 for the y1 for the one value corresponding to one value. But now if I express as a y, x is equal to y, then now I pick this guy, 2 point here. It relate to that x0, that x2. Y, when you express the x as a function of the y, it has a 2 point, which is a double valued function. Okay, so here is 1-to-1 relation. One man has one wife. That doesn't mean that one wife has one man. No, it could have 2 men. Like Saudi Arabia, I heard they have more than one y vice versa. I don't know whether it's analogy is right or wrong. But Indonesia, I'm pretty sure one man has one wife, right? Coastal, right? It is, right? Muslim, yes. No? Yeah, of course. So that's the condition, okay? That's the condition. And first the definitions, and we'll do the example problems. This subscript means random variable is y, okay? Probability density function of y is equal to limit delta y approach to 0. And this is a definition we learned. The probability such that y is between y and y plus delta y divided by delta y. That's the definitions. Okay? Is equal to, I can replace this numerator as a probability such that x is larger than x and the lower and equal to x plus delta x. Delta y carries as is. How can I do that? This is equal to this. How can I do that? What assumption? Single valued function to single valued function, right? So I can do that. So here I just put, because this is expressed as delta x here, this is delta y, I can set delta y approaches to 0, delta x approach to 0. Then here I just carry this guy down here. Then all I did was include delta x and delta x, which cancels each other. Then I can say this is equal to px, which is known from the beginning. Px is known. Y is expressed as a function of x. X is a random variable. Then of course y is a random variable, but we don't know the py. That's what we want to find out, the py. Px we know. Probability density function of x we know. Py we don't know. For example, y is equal to, for example, ax squared. Well, let's say first x. Let's make it general, x squared. This x we know. We have a statistical information on x, but we don't know the statistical information on y. Then we want to find out the y. That's what the question is. And so if you do that, and this guy is equal to, this guy is equal to px. And this is approaches to 0, limit. So this del approaches to differential the d. So this approaches to multiplied by this as absolute. Okay, probability density function always positive. So then px divided by, I can flip this down, py over dx. This equation set is good for the single valued function situations, okay? This simple formulation is a very, very good formulation. But for some case, x is a real n-valued function of y. For the sinusoidal function, what's the n-value? Double, right? For the sinusoidal function, it is a double. If x is expressed as a function of y, so here, double. For x expressed as a function of y, the y expressed as a function of x, it has, for the given for the value of x, it corresponds to that point of y. For this given value, it is that point of y. So this is inverse relation. If x is a function of y, for the sinusoidal function, that n should be 2. In general, you can say just n as is, as I just explained here. So now some example. So example is always better. Example of change of the variable. A sine wave of fixed amplitude x and a fixed frequency f0, that such a sine wave can be considered a random variable if its initial phase angle theta is a random variable. We have done similar kind before. So let's say theta is random, then whole thing is random. So this red color, random angle, then x is random. Okay. Assume the theta has a uniform probability density function, p theta, or you can put subscript theta here also, but I just delete that. This is clear that this p is probability density function of theta. Theta is a random variable. Therefore, you can have a probability function. Say given p theta is equal to 1 over the 2 pi, and the full range is 2 pi. Because I said there, it is theta is a uniform distribution function. When you hear about the uniform distribution function, it's like a step function. It's like a step function means this angle is theta, this is small p, theta, I can put theta if you wish. Then angle limit is, if you're dealing with a whole cycle, you're dealing 2 pi, then area has to be 1. What? The whole area, what's the value of whole area? 1. There's a probability distribution function at that. So what's this to be 1? What this value should it be? 1 over 2 pi. So probability density function is equal to 1 over 2 pi. What's the range of the theta? From 0 to 2 pi. You can put this or you can drop this, doesn't make any difference. As engineers, either way is fine. All other area is 0. Then probability density function is clear. Then question is, what is the sine wave probability density function px of random variable x. For example, the direct function, the x theta is a single valued, but the inverse function is double valued. Over here, you have to be kind of careful. So in the previous page, the y is output is like x is like input. So x here is what? You have the relation wise, you have what? This x is related to, here in this problem, is a theta. And output was a y before, that's a x here. Okay, so which is, before it was a y, x, don't confuse it, now is x and theta. Clear, very clear. And so output was x, not the same as original definition x to y. So it's 2 times, right? 2. N is 2. And this and that. Of course, this will never be 0. If it's a 0 problem, impossible to solve. Undefined. So if you do dx over d theta, then it was a sine before, then it's a cosine. Okay, because nothing to differentiate, only differentiate on this. So you take sine square plus cosine square is 1. So you do this, and 1 minus x goes inside, x goes inside. Then you have a small x square, and probability density function px is dealing right here. 2 times p theta, you know that, which is equal to 1 over 2 pi divided by that value, then you have that one. So this is really, the x is expressed as a function of theta, so this is what you're looking for. This is equivalent to say the y from x and y relation in the definition area. It's a little bit confusing. I want you to really look back after you go back to your office, okay? And this expression, if you can plot it. I want you to plot without, don't turn in, maybe you can show something like Wednesday. Wednesday you can show me, plot it, would you? Using MATLAB, you can plot this function, right? Can you? Jusong, you can plot this function, right? If you plot it, then that's the function to, that's the solution forms for that. This is solution form for the probability distribution function, which is simply you know this guy. So simply integrate from one end to the other. Then you have this. Then you can plot this. You can plot the probability distribution function. You can plot the probability density function. So if you do that, then you have something like this. Okay? Probability density function. This is lowest point. And probability distribution function from 0 to 1, of course. this change of variable, a little bit confusing, because you think usually it's confusing, but nothing to really confuse. I always put, I announced it, always put one problem, as I recall, in the midterm exam. So review correctly. Just resolve the problem. Okay? Nothing much you can do. Just to practice. Okay, so chapter 2 is concerned, is all done. You know, didn't spend much time. So this is good enough to cover the contents of this stochastic process of structure systems. But we will extend into the joint, the probability density function, joint, two random variable. You're dealing with the two random variable, not one. So we deal with the random variable x. So everything works in the plane. Everything works in the plane, not the volume. So everything works something like x and px. Everything defined in the plane. But the joint probability is concerned, you need this third axis. You have x, you have a y, then probability is a function of xy. To do that, you need volume. You need a volume to work with. Okay? And as we have done for the one variable, for the two variable, if it's like a normal distribution function, this end never touches. End never touches, okay? But that's not a big concern for engineer. We can live with it. So that's what we're going to talk Wednesday about this. And Higgy will assign some homework problem. And also, you have also the PowerPoint for this particular file, right? So please just to read before you come in. One area you must review before you come. Really, then it's easy. Anybody read this area? What do you call this? Yunsa, what do you call? Charo, what do you call that? Read this area. It's called the conditional probability. This is only one area you have to pay attention. Conditional probability density function, you have to think a little bit, rather than just a straight reading of a PowerPoint file. All right, Wednesday we're going to do a joint probability density function. Then we'll move to chapter 3. Okay? All right, so this concludes. I think students are waiting usually. So, I'll see you on Wednesday. Here is Augusto. Any question I review, I look through myself, and any questions, see me or Jebam or Higyo, either way. As I mentioned, grading the point is not concerned, really. But if you disagree, you have to talk. Okay, any question, then you have to talk. That's a must. Huh? Otherwise, I'll see you on Wednesday. Okay.